Okay, acid-base properties of ions and salts. So some ions act as bases. These are ions that are the conjugate bases of weak acids, like the hydrogen carbonate ion. So carbonic acid is a weak acid. This is its conjugate base. The conjugate base can become the acid by accepting a hydrogen ion from water. We have to have this ion paired with a counter ion to form a salt. It's like going to some ball or something, some big fancy party, and you can't go by yourself. I know at my kids' school, they won't let you go to prom by yourself. You have to have a date, right? I'm not sure exactly why, but whatever. So HCO3 minus can't come to this solution by itself. It has to bring a partner. Now, oftentimes it'll be sodium or something. I was just giving this idea of activity series and the double replacement reactions to my 1A students. And so for those of you that didn't hear it in my 1A, let's just think about something simple here. Let's talk about sodium chloride reacting with silver nitrate. So you should have learned in Chem 1A that if you have two ionic compounds, you might get a precipitate, and you can predict the products by swapping the ions. So this is sodium ion and chloride ion, and this is silver ion and nitrate ion. And I have this place in my head called chemistry land. And in chemistry land, metals are masculine. So metals are guys, and non-metals are non-masculine, so those are girls, right? And so this is like a guy and a girl going to a party. So we take these two solutions and we mix them in the beaker. The beaker's the party house, right? So we've got sodium going with chloride and silver going with nitrate. And at the party, they mix together, and silver runs into chloride. Silver hadn't met chloride before. They've got chemistry. They really like each other. They like each other so much that they're going to be together the rest of the party. They're going to form a solid. It's going to be a precipitate. And then we've got sodium and nitrate. Like, well, silver and chloride paired up. I guess, we'll talk to each other. But these are, they're like friends. They're not enemies or anything, but there's no chemistry between them. And so these just stay in solution. So we would write this as NaNO3 aqueous. Well, why does this form a solid? It's complicated. It's complicated. It literally is complicated. How did I know that this would form a solid? Because I've memorized the rules of solubility, because I teach them every semester. That's the only way I remember them. Sodium and nitrate, on those solubility rules, sodium compounds are always soluble, no exceptions. Nitrate compounds are always soluble, no exceptions. So this sodium ion is like one of those guys that's like a total playboy, right? He's not going to make a commitment to anybody. He'll hang around with lots of people, but no commitments. And there are women like that too, and that's what nitrate is. She's not going to commit to anybody. So they go to the party, they mix and mingle, but they never get involved in a relationship. And then there are other things like silver. Silver gets into lots of relationships, gets stuck on a person. Now, chloride is often not involved in precipitates, but chloride happens to like silver a lot, okay? So when I look at this equation up here and I see HCO3 minus, so this is the ion that is actually interacting and participating in the chemical reaction. But did hydrogen carbonate come to the solution by herself? No, she brought a cation. And over here, hydroxide ion being formed is hydroxide ion hanging out all by herself. No, now she's hanging out with the guy that HCO3 minus came with. Does it matter which guy it is, which cation it is? It doesn't, because it doesn't participate in the reaction. So this could be sodium hydrogen carbonate or potassium hydrogen carbonate, and then we'll end up with sodium hydroxide or potassium hydroxide. And so we often will leave the cation out because it doesn't matter. But then students will often look at this equation and be very, very confused, because you're looking at the bottle to make this solution and it says sodium hydrogen carbonate. But I just want to put hydrogen carbonate ions in. And so we have to understand that the sodium is coming along for the ride, but the sodium's not going to react at all. So those are called counter ions. Anybody have any questions about that? In the experiment we did last week, in one place it said sodium oxalate, and another place it said potassium oxalate. I forget which was which, but the bottle was one and the procedure was the other. Does it matter? Actually, it does not.
Are counter ions usually like spectating ions?
Yes, counter ions will be spectator ions.
Is it the same thing, or?
It really is the same thing, yeah. So in this equation down here, sodium and nitrate are both spectators because they show up still aqueous at the end.
Yeah.
And so they were present, and they're important because you can't have negative ions without positive ions, but they're not actually participating in the reaction. And so when we look at the net ionic equation, we don't see the spectators. So this really is a net ionic equation where we're not seeing the spectator ions. So if we have sodium hydrogen carbonate and we dissolve that in water, that's baking soda, that's this stuff right here in the shaker, sodium bicarbonate. You dissolve that in water, well, it's a soluble ionic compound. It will dissolve and form sodium ions and hydrogen carbonate ions. Hydrogen carbonate ions are weak bases. So they will react with the water and take some of the hydrogen ions and leave the solution slightly basic. So we can think of any anion as the conjugate base of an acid. So we use A- as the conjugate base of the acid HA, because the acid acts as an acid by donating its hydrogen ion, giving up its hydrogen ion, and then what's left? The A-. That's the conjugate base. The conjugate base can accept a proton, a hydrogen ion, and become the acid again. It's just people, it's like a game of hot potato almost. You know, they're just passing hydrogen ions all over the place. And some things hold on to them longer than others, and some just toss them back at you. So if we look at NO3-, this is the conjugate base of HNO3. I take this anion, I put a hydrogen ion on it, so now it has an H. The H has a positive charge, and so the charge of this changes. I get this, which is an acid. So we can think of any anion as the conjugate base of an acid, but not all of them will act as bases. It depends on what acid they are the base of, right? So here, nitrate is the conjugate base of nitric acid. What kind of an acid is nitric acid? Weak or strong?
Say that again?
Is it weak or strong?
Strong.
It's a strong acid. Strong acid ionizes completely. So for a strong acid, is the nitrate ion that's formed going to take hydrogen ions back? It won't. So HNO3 forms H plus and NO3 minus, and that's a one-way arrow. So NO3 will not pick up a hydrogen ion and become HNO3. It's not going to act as a base. So the conjugate base of a strong acid is pH neutral. It doesn't act as a base. The conjugate base of a weak acid is a weak base. That's not confusing at all. The conjugate base of a weak acid is a weak base. I mean, it's just like, let's throw conjugate and weak and acid and base and just have some word salad, right? The weaker the acid, the stronger the conjugate base. So here we have a strong acid. This is its conjugate base. That's so weak that it doesn't act as a base. If we have something like HF is a weak acid. So it ionizes partially. This equilibrium goes both ways. And so some of the HF will ionize and form ions. And this fluoride ion is the conjugate base of this acid. This is a weak acid, and so that means that this conjugate base is stronger than the conjugate base of a strong acid. Clear as mud, right? Yeah.
So you won't really have the situation where you have either, well, I guess you would have a weak acid and you wouldn't form a strong base.
Correct.
It would be a weak base.
Right.
Neutral.
Yeah, I think, yeah, let's look at this a minute. Just remind me to go back to that other slide. So the acid, the conjugate acids and conjugate bases, they're opposite of each other. So if the acid is strong, then the conjugate base is super weak. It doesn't even act as a base at all. If you have a strong base, its conjugate acid really doesn't act as an acid. And in the middle, you have weak acids and weak conjugate bases. The stronger the acid is, the weaker its conjugate base. Because what they're doing is they're kind of playing tug of war. Oh, look, here's the example that I kind of came up with in my own head. So here's HF, this is the weak acid, and F minus is the conjugate base. And this is an equilibrium, and so there's a balance back and forth, right? So the stronger this is, the farther to the right the equilibrium lies, which means that this one is going to be weaker. So you could kind of think of it as like playing tug of war for the hydrogen ions, maybe. And the stronger this one is, the weaker that one is. Any questions?
So again,
The stronger the acid is, the weaker its conjugate base.
And vice versa.
And vice versa. The stronger the base, the weaker its conjugate acid.
Now, if it's a weak acid, does the conjugate base increase like that?
So if here we've got, pointer. So here we have a bunch of weak acids, right? Some of them are stronger than others. And so here's H3PO4. This is relatively strong, and so its conjugate base is going to be weak compared to the others. So it's sort of an opposite thing. So classify each anion as a weak base or pH neutral. They have to be anions, because in order to act as a weak base in this context, it has to take a hydrogen ion. And that's how we got the conjugate base, was by losing a hydrogen ion. So what we want to do is look at this anion and ask ourselves, what's the acid that it came from? Well, that came from, just slap a hydrogen ion on it. This is our conjugate acid-base pair. What kind of an acid is that? Weak. It's not one of the 6. We don't even need to know what its name is. It's not a strong acid, so it is a weak acid. So if this is a weak acid, then this acts as a weak base.
Are you using those arrows as equilibrium, or are you just
No.
saying, okay?
I'm just saying they go together.
Okay.
Yeah. So ClO4 minus is the conjugate base of what acid? Perchloric acid, HClO4. Conjugate acid base pair. What kind of an acid is this? Weak or strong? It's a strong acid. Because it's on the list, and I told you, remember those guys. Well, if this is a strong acid, how does it affect this as being a base?
It's either weak or neutral.
It's like super weak, right? Because this is strong. And so then this, it is the conjugate base of this, but it doesn't act as a base. And so this is going to be pH neutral. Because the strong acid ionizes completely. This is not going to pick up hydrogen ions. It can't. Any questions? Yes?
Since the stronger the acid, the weaker the conjugate base, if there's a strong acid, would it always be pH neutral?
Mm-hmm.
Because it's so weak
Yes.
that it's basically
Yeah. Because in order for this to act as a base, we have to have this happen where that perchlorate ion reacts with water and forms HClO4 plus hydroxide ion. But is this equilibrium going to exist? No, because this is a strong acid. It only goes, let's see, let me do this. This only goes that way. Because it ionizes completely. None of it is intact. So this can't act as a base because it can't go backwards. Any other questions?
I thought you said they were like opposite, like a weak, strong acid, weak base. And the first one.
The stronger the acid, the weaker the base. When we get to a strong acid, not a stronger weak acid, but an actual strong acid, it ionizes completely. So then the base is so weak that it's not even a base. So we can find the pH of a solution containing an anion that acts as a weak base, but we need to know what Kb is. So if we're looking at the anion, that came from a weak acid. And you can look up acid ionization constants for all kinds of things. They don't generally tabulate Kb for the conjugate base of weak acids, but to do the calculation, we need to know what that Kb is. So I'm going to derive the relationship between Ka and Kb. Hopefully this goes better than the last derivation I did. I'm going to use purple because it's a happy color. Okay, so here I have a weak acid, and it's forming hydronium ions and hydrogen ions. And so I can write an expression for Ka. It's going to equal the hydronium ion concentration times A minus divided by the HA concentration. The water doesn't come into it because it's a liquid. Over here, I've got my anion that's acting as a weak base. So this is reacting with water to make hydroxide ion and this weak acid. So here, this is a base. It's acting as a base. And so I've got OH minus and HA divided by A minus. So that's all very nice, but how do I relate these two to each other? Yeah, so I've got A minus and HA in both of these, right? So if I rearrange them so I get A minus and HA on one side and the other stuff on the other side, then I can say that they're equal. So I'm going to go with, I'm going to start over here with, and I'm going to solve and make this be HA over A minus, just because I felt like doing it. So I'm going to keep these two guys over here, and I'm going to put the hydroxide on the other side. So that's going to be equal to Kb divided by the hydroxide ion concentration. Just rearranged it. And the only reason I rearranged it like that is because it's a little bit like playing chess and you have to think a couple steps ahead of where you're going. And then I'm going to take this one and I'll rearrange it in the same way. I want to get HA over A minus. So in doing that, I'm going to bring HA to the top. I'm going to take A minus to the bottom. And the Ka and the HA are going to trade places. And I'm going to get H3O plus divided by Ka. So now I can say that H3O plus over Ka is equal to Kb over OH minus, because they are both equal to HA over A minus, right? So then they have to be equal to each other. And I can rearrange that and come up with H3O plus times OH minus equals Ka times Kb. And what is H3O plus times OH minus? Kw. Kw equals Ka times Kb. It's great if you can follow that and it makes sense. If it doesn't, you can just remember Mrs. K said that Ka times Kb is Kw. And just go with it. Yeah. It's a little bit like the hydroxide ion concentration times the hydronium ion concentration equals 1 times 10 to the minus 14. Because I told you that's what it does, right? So determining, yeah.
Yes, question. Oh, yeah, on that last slide.
Mm-hmm.
Isn't that, if you just multiply those two together and you cancel out the A's and the HA's, and then it wouldn't be K, A times Kb equals H3O plus times OH?
Mm-hmm.
Can you do it that way? Instead of going around the world like you did there? Does it work like that all the time, or just in this scenario?
Well, I have to get these two equations together somehow.
Yeah, like I'm saying, if you just multiply them both together.
Yeah, that would work, actually. Yeah, I see what you're talking about. What color haven't I used? I haven't used blue. So if I take an equality, like here I've got an equality, and if I multiply both sides by 2, it's still equal. If I multiply it by 2 on one side and 4 divided by 2 on the other side, it looks different, but it's the same thing. So I can take Ka times Kb. This is probably what I was supposed to do, but I did it this other way because that's what came to my head, is going to be equal to these things times each other. Probably. I was just being ornery. No, I just... So if I've got this times this, then the A minuses cancel out and the HAs cancel out. And I've got that, the same thing. Which, yeah, takes up a lot less room. Thanks for asking. Did you like that one better, Vanessa?
What?
Go watch.
Is it because I was making a face?
No, you were making a face about the other one, and so I just did it a different way, and I thought maybe you'd like it better, but you weren't looking, so it's okay. It's okay.
I just know that K and K.
Yeah. Okay.
I just know it.
Okay, so find the pH of a 0.250 molar NaC2H3O2 solution. Ka equals 1.8 times 10 to the minus 5. Okay. Yeah, let's do this thing. So let's orient ourselves first. What are we looking at here? So sodium and acetate. So that's a soluble ionic compound. It's going to form sodium ions and acetate ions in solution. And this is the anion. We're thinking maybe the anion can act as a base. Sodium is just her date, just along for the ride. That's a counter ion. We don't need to consider him at all. So this anion reacting with water can form HC2H3O2 plus hydroxide ion. This is acetic acid. That's the Ka that we've got for this acting as an acid. But I have written this, I'm looking at the anion acting as a base, so I need Kb. Well, Ka times Kb equals Kw. So Kb equals Kw divided by Ka. Okay? 1.0 times 10 to the minus 14, because that's what Kw is, divided by 1.8 times 10 to the minus 5. .5's forever times 10 to the minus 10. I'm just going to call it 5.56. 5.6 times 10 to the minus 10. It's not a very good zero. Okay?
Wait, where did you get the 1.0 times 10 to the negative 14?
That's what Kw is.
Oh. Okay.
But it's good that you asked because there's probably 5 other people that were wondering the same thing. But yeah. 5 to 7. question?
So it's given the 1.0 times 59 14?
The 1.0 times 10 to the minus 14th, see, is what KW is. KW is an abbreviation for 1 times 10 to the minus 14. Yeah.
There we go.
But see, this was an aha moment. And so, we're getting comfortable with each other, right? So it's okay to ask questions because that's how you learn. The stupid thing is to sit there and not understand. You're going to fail, right? So please keep asking questions. Okay, so I got KB. Anybody else? Questions about how I did that? So I have my KB. Now I can make my ice table. So this is, kind of messy. I'm just going to call it A minus. You okay with that? Goes to HA plus OH minus ICE. And A minus is just standing in for C2H3O2 minus because it's a pain in the butt to write. Yes?
And sodium was just a spectator.
Sodium was a spectator. He's just standing around watching people get into relationships.
And that's the clutch.
Kind of a peeping Tom.
It's a weird word.
That's the counter ion to this. And so then if we look over here, hydroxide ion has to have a counter ion. And so sodium would be her partner now. Yeah, that analogy can go to some pretty funny places. Okay, so we have the concentration of this A minus, the anion. So this is the initial concentration, so 0.250 of that. Again, the water doesn't matter because its concentration doesn't change. And the initial concentration of that acid is 0 and the hydroxide is essentially 0. There's always hydroxide ion present in water, but it's in the range of 10 to the minus 7, so most of the time we can ignore it. It's just I am a detail person, and so I can't bring myself to write that it equals 0, because it doesn't. So then we're going to lose some of this as X and make some of this the same amount. And so 0.250 minus X, X, and X. So KB equals HA times OH minus over A. KB was 5.6 times 10 to the minus 10. HA is going to be X, and OH minus is also X, so that's X squared divided by 0.250 minus X.
So, what you were saying earlier about water always containing hydroxide ions, basically pH neutral is like an equal concentration
Yes.
of hydroxide and
Yes. So pure water, a neutral solution of something in water, is going to have hydroxide ion concentration of 10 to the minus 7 and hydronium ion concentration of 10 to the minus 7.
right.
And neither of those is 0,
Right.
but it's not acidic or basic. And that's because water ionizes with itself, which is really weird when you think about it. So, do we think X might be small here?
Yeah.
Yeah. This is a very small constant, 10 to the minus 10, and we're subtracting from 0.25, which is relatively big. So we'll just go ahead with X is small, so we can just ignore that. Square root of 5.6 EE minus 10 times 0.25. Oh yeah. 1, 2, 3, 4, 5. That's a 5. So x is 1.18 times 10 to the minus 5. So if I divide that by 0.25 and multiply by 100, it's going to be way less than 5%. So yay, I found x. What do I do with it now?
Plug it into pH.
Yeah, so this is the hydroxide ion concentration of this solution. I need to find the pH. So this is the hydroxide ion concentration. So what I've got is 14 minus POH. Well, you know what, if you like shortcuts, you'll figure them out yourself. So POH is negative log of 1.18 times 10 to the minus 5. And that should have 2 sig figs if you care. Actually, it has that even if you don't care. And so this is giving me a POH of 4.9281. pH is 14 minus that. .07. Is that solution acidic or basic? It's basic, yeah. The pH is larger than 7, it's a basic solution. Pardon me? 7 is neutral. Mm-hmm. Any questions?
Are there ever positively charged counter ions that have enough of an acidic character to make this not work?
Yes.
Okay.
Yes. We'll get to that.
Cool.
Any questions about this calculation? .07. Awesome. Okay, which anion acts as a weak base? C. So why'd you pick that one?
Because the other ones with an H in front of it would be a strong acid.
Yeah, because HCl is a strong acid, and HBr is a strong acid. HF is a weak acid. Let's just review those strong acids again. You've got HCl, HBr, HI. So those are the halides, but fluorine is the smallest sister. The others are strong, she's weak. Later in the chapter we'll learn why that is. And then there's H2SO4, HNO3, and HClO4. Those are the 6 strong acids. You should memorize them.
Can you go back real quick?
I can go back real quick. Was that quick enough?
Thank you.
It's just once I start writing on the next one, then it gets difficult. Okay, cations as weak acids. So cations can sometimes act as weak acids. And so there's 3 different categories of these. Cations that are the counter ion of strong bases. So examples of this would be calcium, sodium, potassium. Right? Because strong bases like sodium hydroxide, potassium hydroxide, calcium hydroxide. Strong bases ionize completely. One-way arrow. I should have started further to the left. So this is the base, then this is the conjugate acid. Except it isn't, right? So these dissociate completely. Their ions, their counterions, sodium, potassium, calcium, etc., do not ionize water. So if you put sodium ions with water, don't know where that came from. Are you going to get, how would that act as an acid? Well, it's just hard to even think of how it could. Well, I guess the only way would be to make NaOH plus H plus. But is this going to happen? No, because sodium hydroxide making sodium ions and hydroxide ions, that's a one-way arrow. It doesn't go the other way. So these strong bases dissociate completely. Their counterions do not ionize water, so these guys are pH neutral. So this is like the anions of strong acids, right? They're neutral. The cations of strong bases, also neutral.
Can you repeat what you said? I'm sorry.
So the cation of a strong base is pH neutral, just like the anion of a strong acid is neutral. So cation or anion, when you look at its conjugate whatever, if that's strong, then this one does nothing. What about cations that are conjugate acids of weak bases? These will act as weak acids. So BH plus is the conjugate acid of this weak base B. It can react with water to form hydronium ion and the weak base again. And so BH plus acts as an acid. I know. I'll try to say it one more time. I'm not sure if I actually can. Oh, I'm going to say it a different way because there's no way I can repeat that. That's why I'm recording it. So B is a base. We're okay with that? Let's just ignore what's up there and let's think about, well, what happens to B when it acts as a base? We put the base with water. It's a weak base, so we have an equilibrium here. And the base takes a hydrogen ion, leaving hydroxide ions. So here's our weak base. And then this guy is called the conjugate acid. This is the conjugate acid. Because this can act as an acid. Oh, I put the H on the wrong side. Sorry about that. This can act as an acid by donating that hydrogen ion back to something else. Donates it back to water, then we get hydronium ion. So this is acting as an acid. In solution, it forms hydrogen ions. It's an acid.
So it's an acid because it's giving the H plus.
Yeah. So again, it's like, hot potato or hold the baby. Here, the base is going to take the hydrogen ion, the baby, from water, and now it's got the baby. And so now it's not a base anymore because it's holding the baby. And then it can hand the baby back off, and then it's acting as an acid.
The baby's the proton?
The baby's the proton. The base is the babysitter who takes the baby, right? So to act as a base, I'm going to hold the baby for you. Well, now what can I do? Well, I could hand the baby off to somebody else, and that's being an acid. So taking the proton is a base, giving the proton is an acid. So after it's accepted a proton, now it's in a position where it can donate a proton.
And we know that because there was an H cluster.
Well,
Because
when we're looking at this, how do we know that? Is that what you're asking? Yeah. Well, so it's just like what we did with the anions. If we have this cation, we're like, well, that's a weird looking thing. What if I take a hydrogen ion off of it? What do I get? I get B, right? So if this is a weak base, now I have a cation that's the conjugate acid of a weak base. And it can act as an acid.
does it matter? It would be a weak acid, right? 'Cause
It'll be a weak acid, yep. They're both weak. The conjugate acid of a weak base is weak, and the conjugate base of a weak acid is also weak.
if it was a strong base,
If it was a strong base, it would be a pH neutral cation. If it was a strong acid, it would be a pH neutral anion.
okay.
Yeah,
So anytime we see double arrows, it would be weak on both sides.
yeah, yeah. So this arrow here is equilibrium. We have an arrow going to the right, we have an arrow going to the left. The reaction is going in both ways. It's a dynamic equilibrium. So they're passing this hydrogen ion back and forth. Some are going this way, some are going that way. At equilibrium, the rate of both reactions is the same. If we disturb the equilibrium, then the concentrations will shift, but we still have reaction going. When you have a single arrow, like with the sodium hydroxide, that dissociates to sodium ions and hydroxide ions, and they don't get together again. I came with you, but I'm just done with you, and I'm not leaving with you. So a cation is a conjugate acid of a weak base is a weak acid. And we can calculate the pH of the solution by using Ka. Since this is the conjugate acid of a weak base, we probably have the Kb available. But we can pull the same trick to calculate Ka from Kb. It's like exactly the same, but different.
Would you have to know KW?
You always know what Kw is.
Oh, yeah, you're right. Just had that conversation.
Yes, we did.
Nice.
It's okay. I'm going to write it on the board. Kw is 1 times 10 to the minus 14, which happens to equal the hydroxide and hydronium ion concentrations multiplied. Because I said so. My kids won't take it, but you guys have to, right? Okay, so I said there were 3 kinds of cations. The counterions of strong bases, pH neutral. The cations of weak bases, weak acids. And then we have these guys, small, highly charged metals, such as aluminum and iron 3. So Al3 plus and Fe3 plus. These also act as acids. So the ions become hydrated. So the aluminum ion can get 6 water molecules to hang out with it and form this complex ion. When that happens, that thing can act as a Bronsted-Lowry acid and donate a hydrogen to a water molecule, and so one of these is going to lose its hydrogen ion and the others don't. So here we have the metal ion and the 6 water molecules. One of these hydrogen ions can get donated to this water molecule. That makes a hydronium ion. Something that in solution makes hydronium ions is an acid.
Can you say that again?
Something that in solution makes hydronium ions is an acid. You probably wanted further back than that, though, huh?
No, that last
That was-
part was it.
Okay. 'Cause the definition of an acid, we've got 2 of them, but the simplest is something that forms hydronium ions in solution. So we put this in water, it forms hydronium ions, therefore it is an acid. Because it will cause the H3O plus concentration to go up. It'll cause the, yeah. Classify each cation as a weak acid or pH neutral. So, can I remove a hydrogen ion from this? No. How could it possibly form hydronium ions or hydrogen ions? Well, it could make hydroxide, but what's this? Strong base. So this is not going to happen. So this is the cation, the counter ion of a strong base. So what is it? pH neutral. Yeah. Now this guy. What's the magic element in here? The N. It's an amine. Okay, so the rest of it, yeah, whatever. This is it's got a positive charge. It's got hydrogens there. So what if this loses a hydrogen ion? Maybe we'll put it with water and say, is this going to give a hydrogen ion to the water and make hydronium? We end up with CH3NH2. Is this a strong base? No. It's a weak base. Almost said the wrong thing. It's a weak base, right? So this is the cation of a weak base. So it's going to act as an acid. So this one is a weak acid. How about Fe3 plus? Weak acid. Oh. Where's the rest of it? There's the rest of it. I don't know. I screwed that up somehow. How do we know that this is a weak acid?
Small.
It's a small, highly charged cation. So there's two you need to remember. Al3 plus, Fe3 plus. For Chem 1B, yes, that's it. There are others that can do that, but I won't make you remember them on an exam. Okay?
The small highly charged cations are weak.
Act as weak acids. Yep.
A lot of conjugate bases, acids are weak.
Mm-hmm. Yeah.
Too many of the same words all in the same sentence.
Right? And they're related to each other, but you can get the wires crossed so easily.
And they're kind of like, if you look at when comparing strong bases and strong acids, they're almost
Right.
so a cation with a strong base acts as it's neutral.
Mhm.
But a anion of a strong acid
It is neutral. Yep. So there definitely are patterns in there.
you just gotta kind of pick them out.
But the way to get questions like this on an exam correct is to find a way that you can think about it and reason it out for yourself, right? Because just trying to memorize is not going to work. You're going to forget.
Is it always gonna be reacting with water, correct?
Yeah, we can always write it as reacting with water. If you try to memorize these things, like a cation that is the conjugate acid of a weak base is a weak acid. There's another one, an anion that is the conjugate base of a weak acid is a weak base. Yeah, good luck memorizing those things.
I think it helps if you picture like a pH scale and the hydrogens.
Yeah, if you can look at the equilibrium, because written this way, this is acting as an acid. It's donating a proton. But if I go the other way, this B is acting as a base, it's taking the proton. And so whether it's an acid or a base just depends on what side you're going from. Am I starting over here? I'm acting as an acid. If I'm starting over there, I'm acting as a base. And they're both weak. They're both going to happen. When you have a strong acid or a strong base, this is not a two-way street. It's a one-way street. It goes to one side and it stops, nothing else. So the strong acids, strong bases, they don't do any of this funny stuff. It's the weak acids and the weak bases. Come on. There we go. Okay, so let's put those together. Classifying salt solutions as acidic, basic, or neutral. So this gets to your question, Spencer. So the pH of a salt solution, and remember that when we say salt, we mean an ionic compound. The pH of a salt solution depends on what specific cation and anion are there. So if you have a salt, an ionic compound in which neither cation nor anion acts as an acid or base, they're both pH neutral, the solution will be neutral. So the cation is the counter ion of a strong base, and the anion is the conjugate base of a strong acid. Those are going to be things like NaCl, calcium nitrate, KBr. Neither of these can act as an acid or base. They're pH neutral. Salts in which the cation does not act as an acid and the anion does act as a base. So the anion is acting as a base, the cation isn't doing anything, so these are going to be basic solutions. So we have the cation being the counter ion of a strong base, which is pH neutral. The anion is the conjugate base of a weak acid. This is going to act as a base. Then we can have the opposite of that, where the cation acts as an acid and the anion doesn't do anything. Here the cation is the conjugate acid of a weak base, or a small highly charged metal ion like iron 3+ or Al 3+. And the anion is the conjugate base of a strong acid, doesn't do anything. So this is where you might get tripped up with aluminum and iron. Because we do need to remember that these ions act as acids, and so these will be acidic solutions. And then we have the fourth possibility, where the cation acts as an acid and the anion acts as a base. So then what happens? It depends on who's stronger. So you would compare the Ka of the acid to the Kb of the base, and whichever one is bigger wins.
So if Ka is higher, it's acidic, if Kb is higher.
Mm-hmm. Yep. So here's a summary of all of that. Looking at what kind of cation do we have, what kind of anion do we have. We had 2 kinds of anions, we had 3 kinds of cations. If we have the conjugate base of a strong acid, that doesn't do anything. It's neutral. So if our cation is acidic, the solution will be acidic. So we have 2 kinds of cations. If the cation is also neutral, then the solution is neutral. If we have the conjugate base of a weak acid, this acts as a base. We will have a basic solution if the cation is neutral. But for these other 2, where the cation is acting as an acid, it's going to depend on which one is stronger. Okay. Determine if the solution formed by each salt is acidic, basic, or neutral. NaHCO3. Basic. So how do we think about this? We want to look at the 2 ions. We have a cation and we have an anion. This Na+, is that the conjugate acid of a weak base? Or is it the counter ion of a strong base? It's the counter ion of a strong base. So this one's neutral. And then this one, is its conjugate weak or strong? I'll just, since I started doing that, I'll keep doing that. If I add another H to that, is this a weak acid or a strong acid? Weak. The odds are better guessing weak because there's only 6 that are strong. So if you're not sure, go with weak. So if this is the conjugate base of a weak acid, this is going to act as a base. The cation does not act as anything, and so this solution should be basic. Because of the HCO3 minus. Yeah, so this acts as a base because it is the conjugate of a weak acid. And the sodium does nothing. Okay, let's look at this one. That's just looks like a mess, right? So carbons, hydrogens, nitrogen, hydrogen, and then chlorine sticks out. Chlorine is different. This is the anion. So what we've got is CH3 and CH2, NH3, and that's going to have a positive charge, and we're going to have chloride ion. I would expect that to be challenging for a lot of you. Yeah, so seeing the N in there should make us think, oh, that's either a base or a relative of a base, the conjugate of a base, right? So here, this one, when we take the Cl minus off, this has a positive charge. And so its relative is going to be CH3, CH2, NH2. Removing a hydrogen ion, so this is a base. Is it a strong base or a weak base? It's a weak base. The strong bases all have hydroxide in them. So this is a weak base, so its conjugate is a weak acid. So this ion will act as an acid. What about chloride? That is the anion of a strong acid. HCl is a strong acid. So this only goes one way. It's going to be neutral. So I have to identify the two ions and then look at them separately. What does this one do? What does that one do? This one's neutral. That one's a weak acid, so this solution will be acidic. It's getting kind of messy in there.
And it's neutral because the strong acid, the strong base is going to leave the ions.
Yeah. The chloride is going to do nothing because it is the anion of a strong acid. This is the cation, the conjugate acid of a weak base, and so there's some back and forth there. What about KNO3? Potassium ions and nitrate ions. Can potassium ion act as an acid? No. This is the counter ion of a strong base. Potassium hydroxide. So that's going to do nothing. That's neutral. Nitrate ion. What's the conjugate acid? HNO3? Strong or weak? Strong. So is that going to do anything? Nope. So the solution is neutral. Now this last one, I have Fe3 plus and NO3 minus. Well, has NO3 minus changed its qualities since we did part C? No. This is still the anion of a strong acid. It's neutral. Nothing. What's this guy? He's one of those two special ones we need to remember. Small, highly charged, so that's acidic. Yeah.
Is there any case where Fe3 plus doesn't act as an acid?
I think the only time it wouldn't act as an acid is if it was in an insoluble compound.
Okay.
Yeah, then it couldn't. But if it's in solution, it will act as a weak acid. It could get overrun by the presence of a strong base, though.
So it would, in that case, it would just act as neutral?
Well, it would still be acting as an acid if there was strong base present, but its contribution to things would be negligible.
Yeah.
So we just ignore it. So when we've got things mixed together, we have to look at what are each of the individual pieces doing. And like when we looked at the strong acid and a weak acid, we found out that most of the time the strong acid completely overwhelms the weak acid, and both of them completely overwhelm the autoionization of water. And so we can just ignore the smaller things. Any other questions? Basic, acidic, neutral, acidic. I was hoping that was the last one. Which ionic compound forms an acidic solution when dissolved in water? Well, let's look at the ions. NH4 plus, Br minus, K plus, Cl minus, Na plus, HCO3 minus. This guy's related to a strong acid. This is related to a strong acid. This is related to a weak acid. So this is going to act as a weak base. And these guys are going to be neutral. NH4 plus, what's that related to?
Weak.
A weak base. So that makes it a weak acid. What's K plus related to? Strong base. So that's going to do nothing. And sodium, also strong base, nothing. So which is going to make an acidic solution? The one that has the weak acid in it. You might need to go home and watch the YouTube video a couple of times, right?